Hey, physics people. Um, all right, we're gonna do another FRQ, and this one is still on motion. We're still on kinematics, um, and we're just gonna get good at this. So this is a qualitative quantitative, meaning you're gonna have two students that both have like some idea, and then you're gonna pick the one that like, oh, this is right from this one, and this is what he's got mixed up, or this is for student one, student two. So let's look at this. All right, so here is the problem. We got a car and a truck. Let's go ahead and read through this because reading the problem is key. So we're going to go through and read each part. A car is stopped at a traffic light. Okay, this car, let's draw that. So we're going to say this car, its initial velocity is 0. The light turns green at time t is equal to 0 and the car starts moving. So if the car stops, is at a stop, and then it starts moving, that means that it has what happened? Acceleration. It has an acceleration. So for the car has an acceleration. So make sure that we'll do red for the car. Car is accelerating. All right, and it's constant. So we got a constant acceleration. At that instant, a truck is traveling at a constant speed, vt, alongside the car. So the truck has a constant speed. So I don't know how to like change color here. Maybe I can do it here. Oh yeah. Okay, so the truck has a constant speed. So in that case, the truck's acceleration is equal to 0. So the v is constant. So it's traveling at a constant speed. All right, so I'm on that constant speed vt. All right, so and then the front of the car, it's at x is equal to 0, so we're gonna make that the starting point. The truck passes the car, but the car catches up with the truck at the front of the house. So all right, that means that right here, they're both gonna be at the same spot. So this is when the car catches up to the truck. All right, so the truck passes the car and the car catches up to the truck in front of the house such that at TD. So this is going to be, we can put that up here. So that's at this certain time is when they pass each other. So when X is equal to D and the time T to D is when they pass. So for the truck, like notice that if we have a velocity versus time graph, well, if it's not accelerating, then we're going to have it be at a constant velocity. Like in that number could be anything. We could say like, oh, maybe that was at 50 miles per hour. Miles per hour. All right. It could be anything, but it's constant. It means it's not changing. As time ticks on, the velocity is not changing. All right, but well, we can and think about this. The here a horizontal line, the slope is equal to 0. Slope's equal to 0. What what physical constant is equal to 0 for the truck? The acceleration. So the acceleration is also equal to 0. So this is a big key point here, is that the slope of a v versus t graph is acceleration. That is a huge concept that we need to grasp here. All right, so we have that. Now what happens if the car is accelerating? So let's go red here. So now if it's at a constant acceleration, that means that it is got a slope. It's got a slope here. And look at the, so think about this, like it's starting from 0, right? And then the car's picking up speed, picking up speed, picking up speed. So the slope is constant and positive. And so now it's saying that like, oh, it's picking up to 50 miles per hour right here. Well, what happens if the slope is steeper? Well, that just means it hits 50 miles per hour at at a quicker time. So therefore it's accelerating more. So accelerating less, accelerating more. I have this graph. Now I have to graph both of these. So sketch and graph of the velocity of the car and the velocity of the truck as a function of time and indicate any important velocities or times. All right, so this is key. So we have right here the we have a graph and we have 1, 2, 3, 4, 5, 6. We have 6 boxes. So I'm going to, like, one of the key, tricks here is that I'm going to, since there's 6, I'm going to cut that in half and say that this is, uh, that this will be the velocity of the truck. And the reason I'm doing that is because it just makes things nice and even here. So let's go here and let's say, so I have 2, 4, 6, 8, 10, 12. So let's put it to right here. All right, so I'm going to draw the velocity of the truck all the way down to this point right here. And we're going to call that, it's saying like label everything. So this is going to be TD. So remember, this is like the truck's going and then at time D, bam, it hits the house. All right, now here's the tricky part. Now I have to draw the car. So the car, how steep am I going to draw this thing? Well, let's do this. So I made everything symmetrical. So let's count out 6. 1, 2, 3, 4, 5, 6. I put a mark here. And then let's count out the other 6. So 1, 2, 3, 4, 5, 6 at TD. Notice that I went up 3, so everything's going to be symmetrical here. So I'm going to go up another 3. And then I'm going to draw that. All right, so let's do a little analysis here. At TD, they're both in front of the house. And which one's moving faster? Well, here we can see that the car's moving faster. Well, where are they moving at the same speed? Right here, right? So, and this technically would be, since we've counted this out, this is TD divided by 2. You don't have to put this one on there. I think that would be fine. Okay, so I want to talk about something else real quick. So we had the slope of the v versus t graph is acceleration. Well, there's another big thing that we need to think about here. Whoops. All right, the other thing here that we need to look at is that the area under a v versus t graph is displacement. All right, and remember the total displacement was, they called it d. It was like that, the x is going to equal to d. I could put a delta x there. All right, so that the change, that the area under the curve is the displacement, so delta x is equal to d. That means that at both of these, the area under both of these has to be equal to, they have to be equal to each other. At time d, they have to be equal to each other. So think about this. This area under the triangle, let's give it some value. So we have 1, 2, 3, 4, 5, 6, and 1, 2, 3. Well, the area of a triangle is 1/2 base times height. So we have 3 and we have 6. So the area, so 3 times 6 is 18. So the area under here is 9. All right, so this is 9, right? Let's hold off on the area under here real quick and let's do the blue. All right, here this is 3 and this was 3 times 12. So the blue area was 36. So I'm going to write this in blue. So the blue area was 36. All right, so let's think about this. If this was 9, and what would this have to be? What would the area under here have to be? Well, we can do this real quick. So if this was 9, then this section up here would be 9. 9 and 9 is 18. So what's left? And this again is 6 times 3. So this is 18. So they all equal up. 9 and 18 equals 36. So all the areas are the same. So here, all this area right here would equal to all the area under the blue. So that means that they both traveled d, a distance of d. Okay, so let's read on. So there's that. Hopefully we scored some points there. Now let's go to the next part of this. Okay, so the two students are discussing how the speed of the car compares to the speed of the truck when both vehicles are in front of the house. So we looked at that and we said that well, let's see what student 1 says. He says the distance traveled by the car and the truck is the same and the time is the same. So they must have the same speed. All right, let's look at what is right there. So student 1, so what is right? R-I-G-H-T. So the distance traveled by the car and the truck is the same. So this looks right. And the time is the same. Okay, this looks right. So they must have the same speed, but they don't, in front of the house, they do not have the same speed. Come on, okay. All right, they do not have the same speed. And we can look at that on our graph. So let's look at that. Up here at the house, so this is at the house, TD. Do they have the same speed? No way. The red car has gone way faster. It's going way faster because they had to catch up. So, and you can look at that. Everything is symmetrical here. You could say that this is 2 times the velocity of the truck. So there we go. So no, they are not moving at the same speed. All right, so this is what they got right, and this is what he got wrong. Student 2 says, I don't see how that can be. The car catches up to the truck. Let's erase this stuff right here. And let's see what else student 2 says. So it has to be going faster. All right, so student 2 is completely correct. The car catches up to the truck, so the car has to be going faster in front of the house. All right. Okay. So let's go to part C. So derive an expression for the acceleration of the car. Express your answers in terms of d and vt. Okay, so we want it in terms of, want the final answer in terms of vt and d. So for this, I'm going to use delta x here because we're used to our kinematic equations being in terms of delta x. So let's use that. All right, so there are different ways you can come up with this answer. I'm going to show you one. When we go through the rubric does it a different way, and you might think that that one's easier. This is just the first way that popped into my head of doing it, but there's multiple ways to do it. So All right, we want to get d and delta x. Let's look at the car first. Well, we know the car is accelerating. So I'm going to pick a kinematic equation with an acceleration, and I'm going to use this one. So delta x is equal to v naught t plus 1/2 a t squared. Okay, this is an equation on the AP formula sheet, but it's something also that we can memorize. So, so if we look at this, well, the car started off at 0, so right there I can cross this guy out. All right, so there's for the car. Now let's look at the truck. Well, the truck had no acceleration. So whenever something doesn't have an acceleration, that is a really easy equation. Velocity, your displacement over time. Okay, so we have these two. So here though, like in both of these cases, we have time, but we don't want these in terms of time. And we know that at the at like when the delta x is equal to d, when both of these are equal to d, the times are the same. So I'm going to rearrange this equation, solve for t. And so now I'm going to do this. So since the times are the same, I'm just going to come over here and plug this time in to this equation. So since the times are the same, since this is equal to this, like these times are equal to, I'm just going to plug this in. So I'm going to plug in delta x over v of t. All right, so now we are all good with our variables. We have the delta x, which we wanted in terms of. We want to solve for a, and we have the vt. All right, so this is a little bit of algebra. I'm just going to do it quick. So let's look at it like this. So this would be delta x squared. So I can do, let me rewrite it. So let's do this. Delta x is equal to, let's multiply the 2 over here. So I'm going to get 2 delta x is equal to a delta x squared over vt squared. All right, got a delta x over here, and I got delta x squared, so that's going to get rid of one of the squareds. And I want to get a by itself, so then that would be a is equal to 2 vt squared. I multiplied the vt up here, and then I have to divide by delta x. All right, there's my acceleration. So I get acceleration 2 times velocity of the truck squared over delta x. So kind of tricky. And remember, like now we're getting into the harder points. So you don't always have to score these harder points to do well on this. All right, determine the time at which the speed of the car is equal to the speed of the truck. Express your answer in terms of TD. All right, so now I need to figure out how to determine the time. We want to solve for TD. I'm going to pause this real quick. Okay, so this actually is pretty simple. Determine the time where the speed of the car is equal to the speed of the truck. Let's again look at our graph here. So we're going to go back here. And we already said this, that if we look at this, this is when the speeds are equal to everything symmetrical. So that's TD over 2. So that would be the answer for here. Express your answer in terms of TD. So it's TD over 2. Okay, really quickly, let's go through the rubric and see how many points each thing is worth. So Here's the rubric. All right, 1 point earned for a clear horizontal line for the truck. Bam. 1 for a clearly labeled straight line with a positive slope for the car. Bam. And notice that we've labeled TD and VT. All right, so 2 points there. And then 1 point earned for the speed of the car ending higher than the speed of the truck. We had that too. All right, let's go down to part B now. So 1 point is earned for indicating that student 1 is correct that the car and the truck travel the same distance in the time. We talked about that. 1 point earned for identifying a feature of the graph that supports this, e.g. the area under both curves is the same or the visual average of the speed of the car is the same as the speed of the truck. All right, and we talked about that one too. We didn't talk about like that you would actually have to add this, so maybe I made a mistake of not making that clear, that we talked about the graph, the area under the graph. So you would have to put that down for part B. All right, part 2. For indicating that student 2 is correct that the car's speed is greater than the vehicles in front of the house. All right, so we talked about that. And for identifying a feature of the graph that supports the final speed of the car is twice the speed of the truck. So, and we had that clearly on our graph that the car ended twice at the velocity of the truck. I can show that real quick. That the car ended twice the velocity of the truck. All right. I don't know why it repeats here, but part C. Okay, part C, you might want to pause this and look at this. You might like to use this kinematic. They did it really simply. So 1 point for the final speed of the car is twice the speed of the truck. Showed that on the graph. 1 point for applying any other appropriate kinematic relationship. They chose this kinematic equation, which written out, it looks like this. V squared is equal to V naught squared plus 2a. And then remember delta x, but delta x is d at the house. So this is another kinematic equation that we could have used. And they come up with the same acceleration. All right. And finally, let's erase this. And the last part was justifying that t is equal to 2d over 2. And then we can just show that on the graph. That's where the graphs intersect. Okay, that was a long problem. That was big, but I went through a lot of explanations, so obviously it's not going to take you that much time to do that. But we really explored that the slope of a velocity versus time graph is acceleration. That's key. And we explored that the area under a velocity versus time graph is displacement. That shows how far it went. So those are two key things that I want you to keep in mind. Okay, so good job. Hopefully you scored some points. If you didn't, hopefully now you have an idea of how to get those points. All right, yay physics.